So for those of you who just joined us, we are welcoming you to the ISSCC 2025 Circuit Insights. And I have the pleasure of providing you the first talk of the day. My name is Ali Sheikholeslami. As I mentioned, I have been serving as the ISSCC Education Chairs for several years, and I've been organizing this event. The title of my talk is Highlight of the Past Circuit Insights. And I'm deciding on how to choose which material to highlight for you. I had the privilege of seeing all the draft of the slides for this event today. And I thought that it would be nice if I could provide you some background, some material that hopefully help you better understand the material that you're about to see, the flight that you're about to take. I had two observations. One was that obviously we have great speakers today from 5 industries. We have representatives from Analog Devices, from Micron, from AMD, from Broadcom, and from Marvell. And I can tell you that these industries are thinking very highly of you. Just judging by the draft slides that I have observed, some of them believe that you already have a PhD. So in a sense that the content is quite heavy, and I'm again thankful to the speakers for taking my advice and reducing the level, at least for some of you who are still in your undergraduate years. But again, good news is that you're considered already very high level. Please try to enjoy as much as you can. But if you will not follow everything that is being said, the good news is that we're recording this event. You could go and watch them again, right? So let me just go to the next slide. Okay, it all works. It went backward. So as a matter of self-introduction, I already mentioned that I'm Ali Sheikholeslami. I had my bachelor's from Shiraz University in Iran, and I had my master's and PhD from University of Toronto, and I've been a faculty member since 1999. I have been working in the area of circuit design, both analog and mixed signal, in the area of VLSI memory, high-speed signaling, and lately on the stochastic search for global optimum. But as my fun activities, the one that I really enjoy are two. One is that I write circuit intuitions. This is a series of articles for the Solid-State Circuit magazine that is geared towards senior undergraduates and also starting graduate students, and also the Circuit Insights, this event that we're having today. So here's the outline of my talk. I'm going to start from scratch just to bring you all on the same page. I'm going to tell you what is electronics and what is circuit design, and then what is today's program. I'd like to connect everything together. And again, having reviewed all the slides and material ahead of time, I thought that I need to go back to the basics and provide you one of the most fundamental concepts that is going to stay with you, at least if you're going to the area of analog circuit design, and that is the concept of Thevenin and Norton equivalent circuits. So I'm going to go deep down in that concept, and even though you may think that, well, this is something that I learned in my first year or second year undergrads and is never being used afterwards, I will show you that actually this is the most fundamental concept that we have to utilize. And then I will provide you an example which is related to simple voltage follower and flipped voltage follower. These are examples in which I can show you how Thevenin and Norton equivalent circuit could be useful. Incidentally, the last speaker of the day, Vivek, is going to present you with some material that includes flipped voltage follower. So hopefully you will be prepared by the time that his lecture comes in. So what is electronics? Electronics is really the art of controlling electrons. This is what we do. This is what you do. We control electrons for one of 3 purposes. We control electrons in order to store information. And the example of this is this 1 transistor, 1 capacitor DRAM cell. When you essentially open up this valve and allow electrons to go and get stored in this storage nodes. This is how you write in a DRAM. But then how do you read? Well, we need to wait because Dan from Micron is going to talk about how to read and how to write into DRAM cells. But what I want to emphasize here is that this is what we're doing. We're really controlling the flow of electrons to and away from a capacitor in order to maintain information, read and write information. The second purpose for controlling electrons is to process information. Example of this is that imagine you have an information in the form of a signal, let's say a voltage waveform that you have as x of t. What we do by putting a resistor and a capacitor in front of this, we're going to control the flow of electrons that are going through the resistor and being integrated on a capacitor. In doing so, essentially what we're doing is we're doing low-pass filtering of the signal. And again, this is related to controlling the flow of electrons. This time, not using a transistor, but using a resistor and a capacitor. This last one is, the purpose is to communicate information. Again, you can see example of wireless when we use the power amplifiers to mobilize electrons such that they can create an electromagnetic wave. So electrons are used and controlled to create electromagnetic waves. These electromagnetic waves are going to leave your cell phone, go somewhere else, maybe a kilometer away, and at that point, they're going to influence electrons again. And once they're influencing electrons, they're going to replicate the signal or the information that you're sending. And then you can do more processing, such as using a bandpass filter to eliminate noise, for example. We also use electrons, in addition to processing information, storing, and communicating, we use them for energy conversion, such as DC to AC conversion, distribution in smart grids, and utilization, but we are not going to go through that today. So now with this, what is circuit design? This picture shows you that the circuit design is really at the center of our universe. The circuit design at the center is dealing with transistors, with non-idealities, process, voltage, temperature variations, and techniques, circuit techniques. But this is what you do and what you learn in circuit design, and that enables you to apply electronics and circuit design to any of these application areas. So one of them that I have here is memory design. This is controlling electrons for the purpose of storage. And we are very lucky to have Dan from Micron, who has been working in this area for many years, and is going to talk to us about how to view memory design, at least from industry perspective. And then another application we said is related to communicating information. Now, you could communicate information using a piece of wire. This is called wireline communication. And we're very lucky to have Kevin from AMD, who will talk about wireline communication. And then we go to wireless communication. That is what we use also in many applications, such as cell phone. We don't use wires anymore. And that is a lot of tricks and a lot of great concepts in the area of wireless. And that is going to be covered by Human from Broadcom. And then we can see the light at the end of the tunnel, and we're going to go to optical communication. That is a very fast advancing area of communication, and we are very happy to have Vivek from Marvell who will be covering this for us. Please remember that these are not the only areas. This is what we could potentially fit in one day of Circuit Insights. There are, for example, machine learning and AI, and we had talks in the past Circuit Insights that went into it. We can go into computer hardware. All of that is also controlling electrons for the purpose of processing and calculation. We can see electronics in the area of human health, and all of these are considered circuit design. These are the applications that you're dealing with. But underneath all of this, there's also electronic devices, the transistors themselves. And if you know, there's another whole society that's called Electronic Devices Society, and they're looking into transistors and how one individual transistors can be designed in order to be used in circuit design. And your job as a circuit designer is to act as a great interface between the transistors that are sitting at the very bottom and all the applications that you will see emerge from the circuit design. So as such, you're not just looking at circuits, you're not looking at transistors, you really have to gain an understanding of the system level. You need to understand, if you go to the area of wireline, for example, it's full of concepts in information theory and in noise, signal-to-noise ratio, all these concepts that on their own could be research topics for many professors, but you need to understand them. If you go to the area of wireless and you deal with noise, there's a lot of random processes involved. You have to learn all of those and understand circuit design, and you need to know how to utilize transistors that are characterized for your use. So you're really at the center of the universe here as a circuit designer, and I hope you will enjoy that ride. So just to delve a little bit into this at the center on the circuit design, You all know by now you've seen in your second and third year undergrad that the transistor has a nonlinear characteristic that is shown here. And what we do typically in analog circuit design is we're trying to bias the transistor at a certain voltage and current, and then we would only utilize the transistor in a very small range of input voltage such that the action of the transistor can be linearized. So we can use the transistor as a linear element, and we will be using this, of course. But the fact is that there will be always time when that input voltage becomes slightly larger than what you like. What happens in that case? Or there are applications in which linearity is so important to you that even a small deviation is considered too much. Now we need to go and study nonlinearity and how do you characterize nonlinearity. And so that is one important opportunity for circuit innovations for us to see how do we deal with nonlinearities. Then you look at this circuit here, which is a typical diff pair or differential pair, where you would like to have two transistors that are fully matched. We like to have two resistors that are fully matched. But then you learn more about device physics and the fabrication, and you find out that even though you would like these two transistors to be the same, in fact, there is a random process at play. These two are never identical. There will be some deviations. In this case, I'm showing deviation in the threshold voltage of the transistors. How do you deal with that deviation? As soon as they are not matched, they're going to cause problems for us, right? And the resistors are not identical. How do you design in the face of variation? And again, as I mentioned, we're very happy to have Roberto with us from Analog Devices, who has been working in this area for many years, and he will tell us how to deal with this. Roberto will also talk about parasitics. When we're dealing with transistors, there are these parasitic capacitances. And of course, there are like parasites, something that we don't like. We like to eliminate them. But of course, sometimes you have no choice, and in this case, we don't have a choice. The question is that how do we design the circuit in the face of parasitics? Or how do you sometimes even utilize that parasitics to your advantage? This last one I'm showing is related to noise. The fact is that electronic devices such as resistors and transistors, they create their own signal that are unwanted. Even if there's no input to the system, the circuit is creating noise. And the question is that how do we deal with noise? Noise, of course, is a random process. This is what I mentioned, that you need to really take a course in random processes to really appreciate what is happening, but we do not have a choice. We need to understand how transistors and resistors behave when it comes to noise, and then how do we utilize that to understand the overall concept. Again, we are very lucky to have Houman Darabi from Broadcom. He's been working with noise most of his lifetime, and he's going to talk to us about this. So we're very lucky to have him with us. Now, as I mentioned, memory, we look at the circuits in memory. This very simple back-to-back inverter is going to do magic for us. It's going to read data from a cell and tell us whether that data is 1 or a 0. And again, I would leave this to the able hands of Dan, who will explain to us how this works. So please look out for this as we talk about sense amplifiers. In the area of wireline, you think it's easy. You just have a transmitter that creates 0 and 1. You have a piece of wire, and then you have a receiver. How could it get wrong? Or difficult, for that matter? And of course, Kevin is here to tell us, hey, wait a minute. Even if I have 1 inch of line, just 1 inch, okay, or 2 inches, and you want to send bits that are zeros and ones, but they are at the rate of 224 gigabit per second. If you have 200 millivolt peak to peak of the signal here, if your 1 and 0 are distant by 200 millivolt, by the time they get here, even though it's just 2 inches away, they become 1 millivolt peak to peak. The signal gets heavily attenuated. 1 millivolt, and just to tell you how much is 1 millivolt, that is the level of noise that you have at that point. So your signal and noise are essentially mixed together. How would you ever be able to tell me what was the data that I sent here when the noise from these devices are at the same order of magnitude in terms of the voltage swing? And that is the art of designing for wireline. In addition, you will see also noise playing a major role here. This last one is optical communication. And so this is maybe a way to address the issue that the electrons that go through the piece of wire at that high frequency are getting heavily attenuated. And so I cannot go longer distance, because if the signal gets attenuated that much, I don't have much luck to go across this room, let alone going across the ocean. And that is when we resort to optical communication. So Vivek is going to tell us that he uses a device that's called a Mach-Zehnder modulator. He will essentially use these two arms, and he will change the refractive index of these two using electrons in order to create, to modulate intensity of the light. So the light is now either, let's say, very intense or dim, and you can use that at a very high speed and be able to go far distances without really having much attenuation. So this is the area of optical communication, and this would be the last talk of the day. So in a nutshell, what I'm going to do is I'm going to provide you some background and highlights, and then we go to circuit design with process variation, memory circuit design, excuse me, and three area of communication, which is wireline, wireless, and optical. So here's the outline of what I'm going to talk about. As I mentioned, I would like to focus on one very important concept, and that is Thevenin and Norton equivalent circuit, and then I use an example of it. So, you know, this idea of undergraduate studies and circuit and understanding circuit in an intuitive way is something that I've been working on for many years. In fact, I've been writing articles on this for the last 10 years, since 2014. This article that says looking into a node is, in fact, what I would like to cover for you today. But all of these circuit intuitions articles and circuit insights are obviously available to you on the web, so you can access them easily. Okay, so as I said, I'm going to talk about Thevenin and Norton equivalent circuit, and then I go to an example of using it in flipped voltage follower. So what is Thevenin and Norton equivalent circuit? So this picture essentially tells you that, imagine that you have a linear circuit which includes resistors and voltage sources. They could be dependent or independent, but the assumption is that all the elements are linear. And for simplicity, I'm assuming that we only have resistors here, but obviously you could have capacitors, you could have inductors, any element that's considered linear. And the load, though, that is showing here, the load could be linear or nonlinear. That doesn't matter. What the Thevenin equivalent circuit theorem tells you is that you can replace all the circuit, doesn't matter how many resistors, sources you have in there. You can make an equivalent circuit that does exactly the same to the voltage and current of this load if you replace it with a single voltage source in series with a single resistor. Again, we're looking at resistor alone in this case, right? Resistors, dependent current sources, dependent voltage sources. You can replace the entire circuit with a single voltage source in series with a single resistance, which we call equivalent resistance. That is the Thevenin equivalent circuit. We could also do Norton equivalent circuit for this linear circuit that we have. And in this case, instead of having a voltage source in series with a resistor, we could make it into a current source in parallel with a resistor. That is the essence of Thevenin and Norton equivalent circuit. Again, I'm sure you've seen this in your first or second year circuit theory course. And here's a bit more practical way of doing this. So if you would like to find that voltage source in series with a resistance, in other words, when you want to find out the Thevenin equivalent circuit, this is what you do. You start with your original circuit, right? And then you zero all the voltage sources, independent voltage sources, and all the independent current sources. So you can see I go from here to here. Now I no longer have a current source or a voltage source. I only have dependent current source and dependent voltage source and resistors, right? There's no independent source anymore. And then I go and, in this case, I find out what is the voltage that I can see. I'm sorry, I made a mistake here. The two steps. In step one, I need to measure the open circuit voltage. So you have a load that was connected here. You remove that load, but you do keep all the sources intact inside the circuit, and you measure the open circuit voltage here. So this voltage, this open circuit voltage, turns out to be your Thevenin equivalent voltage source that I will use to build the Thevenin equivalent circuit. But then to measure the R equivalent, I need to zero all the independent sources, and I'll look into this terminal or this port, and I will find out the resistance here is R equivalent. In other words, there is no independent source here, so all this represents is a resistor. And that will be R equivalent. We put them in series, and now we claim that this circuit behaves exactly the same as this circuit. For the case of Norton equivalent circuit, what we need to do is to short the load. So if there was a load here, we remove the load and we short it instead, and we measure the short circuit current that goes from one terminal to the next. We call that I short circuit as a function of T. We find the R equivalent the same way as we found it here, and then we put them in parallel. And so obviously what we are saying as a Norton equivalent circuit is this is equivalent to this is equivalent to this, and therefore these two are equivalent of each other. And they are governed by the fact that the ratio of these open circuit voltage to the short circuit current should also be equal to R equivalent. So that is what you've learned in the past. And now I'd like to bring you up to speed with the concept of transistors. So when we look at a single transistor, I'm using an NMOS transistor here. You have learned, perhaps in your third year undergrad, that for small signal analysis, this transistor can be made equivalent to this circuit. And you can see here, you have the gate and source here. Again, this is only for small signal purposes. You have gate to source here. You have a dependent current source. This is a voltage dependent current source, which is GM times VGS. And you have GMB times VBS. And you have an output resistance, which is RO. So that means the transistor that we were looking at, and it was a nonlinear element, if you're using a certain bias point, and if you're using a small signal, then it can be considered as a bunch of linear elements. You can see all of these elements are linear. This is GM times VGS. There's no VGS squared anymore, for example. And this is GMB, which is related to the body effect. These are the short circuit transconductance of the transistor. This is GMB times VBS and then RO. So we're going to just use this model now when we deal with transistors. And this is the one article that I mentioned, that you can now look at transistors in light of this small signal model. For example, I've called them library element in that article. That means you're dealing with transistors that are always in one of these configurations typically. And as soon as you see them, you can therefore replace them by that equivalent circuit. So look at number one. Library element number one tells you that if the source and drain are grounded, then looking into the gate, you see an infinite resistance. Now remember, what we are assuming is that this transistor is operating in the saturation region. All of these transistors that are shown here are assumed to be operating in saturation region. But for small signal purposes, we've removed all the DC, and we're only looking at the small signal voltage and currents. So under that circumstances, even though the drain seems to be connected to ground, it could have been a DC voltage, but we grounded it for a small signal, right? So in this case, the R equivalent is infinite. Now we go to library element number two, and here is an example where the gate and the source are small signal grounded, and we're looking into the drain of the transistor. What we see in this case is also a resistor, but the value of this resistor is RO of the transistor. You go to library element number three, you look into the source while the other two are grounded. And in this case, you see RO in parallel with 1 over GME. By the way, GME is the effective transconductance, which I define as GM plus GMB to make life easier for us here. Library element number four relates to a diode connected transistor, and the idea is that if you have the source grounded and the drain and gate are connected together, what is the equivalent resistance looking into the drain? And in this case, you will see RO in parallel with 1 over GM. Now, one thing about these four is that there's no voltage source or independent voltage source or current source here. That's why the only thing you see is a resistor. This could be expanded to library element number 5 and 6 when you decide to put a resistor in the source. This is called resistive degeneration. And in this case, when you look into the drain, you find that the R equivalent here is RS, which is the resistor in the source, plus RO plus GME RORS. In a sense, what this circuit tells you, at least when GMRO is much larger than 1, is that this configuration can take a small resistor and could multiply it by GMRO and show it off at the drain of a transistor. So you essentially have a resistive multiplier. If you look at number 6, you're looking into the source, we put the resistor in the drain. You can think of this as a resistive divider. If you have a large resistor in the drain, for example, you will find out that this RD effectively is divided by GMERO in the circuit. Now, again, for library element number 1 to 6, there is no source. Therefore, what you see is a single resistor. All of these are equivalent to a single resistor, and their values or parameters are given here. When you put a source here, such as Vin, what I'm trying to say here is that now if I look at the output node, and in this case is the drain node, what I see is either a Thevenin equivalent circuit or Norton equivalent circuit. That's all there is to it because this is a linear circuit. So what happens in this case? In addition to the R equivalent that I found here, I also see either an open circuit voltage or a short circuit current. And you can easily find out what are those open circuit voltage or short circuit current. If you look at number 8, when you have an input voltage connected to the gate and you're looking into the source, you also see either Norton equivalent circuit or Thevenin equivalent. If you want to see it as a Thevenin, as a Norton, you will see I short circuit is equal to this. And if you want to see it as open circuit, you just multiply this by R equivalent. I did not write R equivalent here because those are shown on top. To find R equivalent, you need to ground Vn. And once you ground Vn, this becomes exactly this, and therefore you have the value of R equivalent in this case. So obviously, it may take a bit of time to get used to these library elements, but once you master them, it will make life very easy to analyze any large circuit, and I will show you 2 examples of this. So first of all, I want to tell you, how did I drive this? I mean, it looks a bit complicated. Even look at this. How does the output will look like this equation? And I wanted to show you that you can actually do some easy transformation on the circuit and be able to see it. So for example, here, what I'm saying is that, well, if they have RS here and this is GMRO, I can replace this by the equivalent circuit of the transistor. So essentially the transistor is GMEVS in parallel with RO. After some minor manipulation, you'll see this is equivalent. Now I change this into a Thevenin equivalent circuit, only this portion of the circuit, and I will get this. And then I see here that this voltage source, which is the dependent voltage source, is producing GMERO times VS, where VS is the resistance that is shown here. So given that these guys are in series, the current is the same. And for this guy to produce a voltage that is GMERO times the voltage across this, that means this is equivalent to a resistor whose value is GMERO times RS. So you see now there are 3 resistors in series, and when you add them up, you will get the equation that I showed you on the previous slide. So you can do this on every single library element that I showed you, so you can actually see that this is in fact a resistor, even though it looks like a dependent voltage source. Now, one more trick that I want to tell you, this would be very useful, especially if you're writing quizzes or exams. It's really useful. If you have a linear time invariant circuit and you're trying to find the voltage of a node, sometimes the easiest way to find the voltage of a node is to short that node to ground. It kind of looks counterintuitive because if you are scared probably to short a node to ground, you think it will be a voltage, whatever. But this is just a practice to get the theoretical voltage of that node. So what you do is that you short this to ground and you measure or you calculate the value of I short circuit. So this is step number 1. And step 2, you look at this LTI circuit and you ask yourself, what is the equivalent resistance looking at that node? And remember, to do this, you need to zero all the sources inside. Once you have I short circuit and R equivalent, you just need to multiply them and you get the voltage of this node. This is the direct consequence of Norton-Thevenin equivalent circuit. When you're trying to find a V node, you're really trying to find the open circuit voltage. And instead of doing this, you can short this to ground, multiply by R equivalent, and you'll get the same result. Now let's see this in action in this case. So this is an example of a resistive DAC. We have a lot of examples of DAC that is coming up later today, so I thought this may be useful. If you look at this, I have V0, V1, V2, and V3, and you have binary weighted resistors, R, 2R, 4R, and 8R, and there's 8R here. And I'm interested in finding what is output voltage as a function of these input voltages, right? Or you can consider them as input bits, right? These being zeros and ones. Well, you can write KVL and KCL and solve it, but I like to use the technique that I just taught you. And that is, to find the voltage of this node, you short this to ground. If you short this to ground, you see what life becomes so easy. This 8R goes away because both ends of 8R is grounded. And the current that goes to ground here is V3 divided by R, because remember, this is grounded, plus V2 divided by 2R, V1 divided by 4R, plus V0 divided by 8R. So that is I short circuit. You can immediately write it without writing KVL and KCL and trying to solve equations. You just write it. And then you need to find out what is R equivalent. To find R equivalent, we need to ground or zero all the voltage sources. So that's what you get. And you see, now we have 5 resistors in parallel. So it's easy to see 8 in parallel with 8 gives you 4. 4 and 4 gives you 2. 2 and 2 gives you 1. 1 and 1 gives you half. So this is R over 2, right? So this is the equivalent resistance. And now let's multiply. When you multiply these two, you will get this times R over 2, right? So R gets canceled, and this is what you'll get. And this is exactly the operation of a DAC, a digital to analog converter, when you get V3, V2, V1, and V0 being the most significant bit and the least significant bit of a 4-digit word, and you turn them to an analog voltage and you find it. So I showed you this because it shows you that this technique of shorting a node to ground will literally save you time and will be able to show you how to get to the answer very quickly and intuitively. Here's another circuit. Looks a little bit more complicated, but same concept. So you've seen the differential pair with two transistors, 2 resistors, and a current source at the bottom. I've now zeroed all the DC sources because I'm interested in the small signal voltages in this case. And in particular, in this case, this is ground, and I have a small signal voltage Vn applied to the gate on the left. And what I like to find out is that, for example, what is the voltage of any node? And as an example, I choose this node, Vs. Now remember, you can always go and replace these transistors with their small signal equivalent and write KVL and KCL and solve them, but that doesn't give you any intuition and understanding. Instead, try to short this node to ground and find out what is the short circuit current of this node and find the equivalent resistance. And that is very easy to do. So if I short this to ground, you realize that this transistor goes away because all of its terminal is grounded. This side goes away because everything is connected to ground. So you're really dealing with this and you're asking yourself, what is the short circuit current to ground here? And because you have input, which is gate is Vn, source is grounded, you have VGS, you multiply by GM, you get the current here. If you want to consider RO here, there would be a current divider or resistive divider for currents, and you can easily write the equation for I short circuit. To find R equivalent, that's easy. You also need to ground this, and then you see the resistance looking down. The library element tells you is RO3, looking up. So you get these 3 resistors that you could easily calculate, and you put them in parallel, and that gives you this R equivalent. And then you multiply. You have the value of the voltage of that particular node. And with that, you can now do a lot more. Okay, so this was the basics of Thevenin and Norton equivalent circuit and how we could apply them to transistor circuits. Now let me move on to the example that I like to highlight. So I start with a simple voltage follower. Simple voltage follower is using one single transistor here. When we have input voltage applied to the gate, and I assume that I like to bias this transistor with a bias current of IB, and I assume that my load is capacitive in this case. There's a capacitive load, CL, and I like to find out what is the voltage that I will get here. What is the voltage gain from input to output? So to do this, the first step, of course, is to zero all the DC as we mentioned. So this VDD becomes now grounded. The IB becomes 0, it will go away, and you end up with this simple circuit. And in order to find out what is the ratio of output voltage to the input voltage, I use the technique that I talked about. I like to short this to ground, measure output impedance, and multiply the two. So if I short this to ground, I will see that it's very easy because now VGS is equal to Vn, and all I need to do is to multiply it by Gm of this transistor. So I short circuit is equal to Gm Vn. Very easy. Now what about the output resistance that I like to see? Again, I consider CL as a load, so I keep it aside. This doesn't come into equations. So I just need to look into this and ask myself, what is the output resistance? looking into this node. And this was one of the library elements that I showed you. Looking into the source of a transistor, you will see 1 over GME in parallel with RO. So if you put that here, and if you make some simplifying assumption that, for example, you don't have the body effect because you're using advanced technology that doesn't have body effect, and you assume that 1 over GM is much smaller than RO, essentially what you're saying is that the equivalent resistance looking at the source is 1 over GM. And therefore, you multiply these two together, and you get V out over Vn approximately being 1. So this is exactly what the voltage follower should be doing. It should follow your input to the output with a gain of approximately 1, but sometimes slightly less than 1. And the important part is that it should have a low output impedance. And the low output impedance in this case is 1 over GM. And as you know, 1 over GM typically is small. So let's say less than 1 kilo ohm. And that may be good enough for you to handle the capacitance that you have. But the question that we like to ask here is that, okay, so we have a very simple voltage follower. But it seems like the output resistance is 1 over GM, and I said 1 over GM could be in the order of, let's say, 1 kilo ohm. What if I need lower resistance, right? How can I accommodate lower resistance? And that is the concept of moving to what is called a flipped voltage follower. So let me walk you briefly through this flipped voltage follower in case you haven't seen them. Again, as I mentioned, this will come up in the last lecture of today, so I want you to be prepared for it. So if you look at this, the difference between these two circuits is that, first of all, we just had 1 transistor. Now we have 2 NMOS transistors. We also notice that this current source that we have here, the bias current, instead of provided from the bottom, is provided from the top. This is, in fact, the only reason why this is called flipped voltage follower, because the current source that you have at the bottom that was trying to draw current from here is actually pushing current into the circuit. So the current source the bias current went from the bottom to the top. And this is what we called it flipped compared to this. That's the only reason why it's called flipped. But now let's look at the properties of this. So if you look at this simple voltage follower, it seems like the current that you have through M1, the total current through M1, is equal to IB, which is the bias current, plus the current that goes through the load. Now, the load current is going to change according to the input voltage. So this load current is going to change. This is constant, but the sum of the two are going through the transistor. So that means your transistor doesn't have a fixed current. That current is going to fluctuate a little bit up and down, right? And it seems like this transistor is trying to do two things. It's trying to follow the voltage here, but at the same time, it's trying to provide current to the load. And these two jobs are really hard to do at the same time. So what we do is that when you go to a flip voltage follower, you realize that the current through M1 is always constant. This IB is the one that is going through M1 and M2. And the current that you need for CL is actually provided by M2. So it appears that M1 that is doing the voltage following has a fixed current. And remember, in saturation region, if you have a fixed current, you should have a fixed VGS, at least the first order approximation. And so the voltage really what you provide here with a VGS DC lower, you will get it at V out. But what about the current? The current is provided by M2. So we did two transistors and we divided the task of voltage following and current delivery to two different transistors. Now let's see that in more detail in the next slide. So what I want to find out is that, so what does it do for me? Does it really reduce the output resistance? That's the goal, right? So what I'd like to find out is that, first of all, what is the short circuit current in this case? If I find a short circuit current from output to ground, and then I find the R equivalent and I multiply. That was the technique that we talked about. So to find out what is the I short circuit, remember, I need to remove all the DC. So that DC current source that was at the top is now removed. I'm looking only at the small signal input Vn, and I want to measure what is I short circuit. If you look at this, even though it looks complicated, it's actually very easy because this transistor M1 has a gate connected to Vn, source connected to ground, and it has zero current. Why does it have zero current? Because this transistor is connected to the gate of this transistor, and the gate is open circuit. So there's zero current provided by M1. That automatically tells you that M1 is nothing to do with the current. So if there's zero current here, what I could do is redraw the circuit easily into this form. So you can see M1 shows up here. Gate is connected to Vn. Source is connected to ground. There is zero current here. And the drain of this is feeding to the gate of M2. So that's the gate of M2. And now the drain of M2, which provides us the short circuit current, is connected to ground. So this is now very easy to analyze because you can use the library element. You can, in fact, can find out what is VD1 through the same technique, and you find out that that is minus GMRO times Vn, and this minus GMRO times Vn is going to be multiplied by Gm of this transistor, so you end up with a total or effective short circuit transconductance, which is GMRO times Gm. So if you recall, in the previous circuit, in simple voltage follower, we just had Gm. Now what happened is that short circuit current is multiplied by GMRO. And we want to see what happens to the output resistance. So if you look at the output resistance, again, same concept, and you apply now a voltage source, you want to measure the current. For the same reason, the current that goes here is 0. You only see the current here. You can find the voltage of this node, and then you will go back here, and you find out I2, and then from the division of Vx and Ix, or I2 in this case, you will get this equation. So this tells you that the output resistance now is no longer 1 over Gm that was before, but is 1 over GMERO times 1 over Gm. So what we have done is that we have really increased the short circuit current by a factor of GMRO. At the same time, we have reduced the output resistance by GMRO. Increase one, decrease the other one. The product of the two, in fact, remains the same. So if you look at this, I don't know what happened here, but if you look at V out over Vn, we need to multiply those two. For a simple current, for a simple voltage follower, we have approximately a gain of 1. For the flip voltage follower, when we multiply this short circuit current, which is Gm times GMRO, times the output resistance, we also get 1. What happened here is that this Gm, which was the short circuit current or short circuit transconductance, go from Gm multiplies by GMRO, but the output resistance is divided by GMRO. That is exactly achieving the purpose we wanted. We wanted to have a buffer that goes, or voltage follower that gives a gain of approximately 1, but we wanted to reduce the output impedance. And to reduce the output impedance or output resistance, we went and we increased the short circuit current, and therefore we got the smaller output resistance in this case. So what is the advantage of doing this now? What can this enable us? Remember, there is a capacitive load here. And so the RC time constant of this node that determines the speed of the circuit is going to see a much smaller resistance looking this way than this one. This was 1 over Gm. This is much smaller by a factor of 1 over GMERO. And therefore, this circuit now can work at higher frequencies. And this is what you will see later today. You can probe this further. In fact, I've just touched the surface here. You can look into what is called super source follower. Just instead of using NMOS and NMOS, you can use NMOS and PMOS, and you find out same properties. Or you could go further and you look at class AB super source follower. And these are actually 4 parts of the articles that I've written for Solid State Circuit magazine. So you're welcome to look deeper into this if you're interested. In terms of other ideas, there will be a lot of talk about noise today, so I wanted to invite you to please look at intuitions and insights on noise and distortion. And these are 2 other articles that, or I guess this was done in the Circuit Insights, but also there are corresponding articles on this for your pleasure of understanding. Here's a summary of what I talked about. So we said, when you look into a node, we see either Thevenin or Norton equivalent circuit. As long as you have, assuming that the circuit is acting linear, which is the case for small signal. And this is not just for the first 2 years of undergrad. It goes all the way to your PhD. You could utilize this. This is all you need. Also mentioned that if you want to measure the voltage of a node, it's always, or not always, but most of the time, much easier to short that node to ground, measure short circuit current, and multiply by the equivalent resistance. I mentioned that in simple voltage follower, 1 transistor is used to essentially do both voltage and current delivery. Whereas when we went to flip voltage follower, we get the same gain, but now the output resistance is going to be much smaller, and we could do essentially the same voltage and current delivery, but using 2 different transistors, and that will enable us to reduce the output resistance significantly. If you would like to look more into this, there are many resources on ISSCC. So I would like to highlight here some of the articles in the magazine that is accessible to you. These are the circuit intuitions. These are Circuit for All Seasons and the Analog Mind that are written by our colleague Behzad Razavi. And Chris Mangelsdorf, he has an article that's called Shop Talk, What You Didn't Learn in School. So I think this is a very useful read for you. The ISSCC YouTube channel is available to you, and you can go ahead and look at this. All the articles on circuit intuitions, I've summarized them on my website. So if you look at this, you will see link to all the past circuit intuitions. If you would like to have access to all the past circuit insights videos, and you find it hard to find here, you can also find them on this website. In addition, there's ISSCC Resource Center, and that is collecting all the past ISSCC tutorials. These are a slightly higher level, and you need to be a member of ISSCC Society in order to get access to those. But I highly recommend them to you if you are a master's or PhD students and later. With this, I'd like to acknowledge the members of my team at the University of Toronto. I'd like to really thank my own undergraduate students at the University of Toronto for asking me great questions and inspiring me to explain these concepts to you. I'd like to thank the readers of Circuit Intuitions articles for their great support and suggestions, and the Solid State Circuit Society for sponsoring this event and many other educational events. This brings me to the end of my talk. Thank you very much.